Hey, in this tutorial, we're going to be looking at section 6.5, which is all about curve sketching. Okay. So, stationary points, they occur when our derivative, f dash of x, equals 0. Okay, so we've got a little table here that talks about the nature of our stationary points. Okay, so if we're saying at some point, for some value of x equaling a, our derivative equals 0, okay, then for all values less than a, okay, our derivative is negative. Okay, we've got a negative gradient. Okay, for all x values bigger than a, we've got a positive gradient. We can see here that we've got a turning point here. You can see with the shape, that would be a minimum turning point. Okay, if we had, again, our gradient equaling 0 at a, okay, then for all our x values less than a, our gradient is positive, and for all values greater than a, it's negative. Then you can see that we get a maximum happening. Okay, if our gradient is negative for all values less than a, and also negative for all values greater than a, then what we have is a stationary point, or a point of inflection, sorry. We come down like that. Or we could also have it where below a and above a are both positive. So we have another point of inflection. Okay, so we'll keep moving on. Okay, so really we're up to a worked example. Okay, so determine the stationary points of f of x equals 2 plus 4x take 2x squared take x cubed, that should be x cubed. Okay, and justify their nature. Okay, so the first thing we need to do is go, okay, well, f dash of x, okay, well, 2 is going to drop out. Okay, so I'm going to be left with 4 minus 4x minus 3x squared. Okay, so we can factorise that, and we get f dash of x equals 2 minus 3x and x plus 2. Okay, we can factorise it to get that. Okay, so we need to know when it's equal to 0, so hence why we want to factorise it. So we can use our null factor law and say, well, it's going to equal 0 for 2 take 3x, or 0 for x plus 2. Okay, so x is going to equal 2 on 3, or minus 2. Okay, so we've got our values there. So what we do is we make what we call a gradient table up. Okay, so we put in the values that we know. Okay, so we've got our minus 2, and we've got our 2 on 3. Okay, so we'd probably select, say, minus 3 over here. Okay, we'd probably select minus 1 here. Probably 0 there and 1 here. Now technically I've probably included one more point than what's needed. Okay, in terms of, we probably only actually needed 1 point in between, but what you've got to be really careful of is where you take your points. For example, if we had a graph like this, okay, we know we've got our points there, okay, and you choose a point here, but you go too far across on this one and choose a point here, okay, then you're going to think it's a point of inflection, because you're going to say it's positive 0 and then positive again. Okay, but it's actually not, it's only a maximum, okay, because we should have taken a point in here. So you just got to be very careful about where you choose your points. Okay, and always have in the back of your head, what's this supposed to look like? Well, it's supposed to be a cubic, that sort of thing. So we'd expect something to be similar to that. Okay, because we know if we've got a point of inflection, well, we'd only actually have one x value for where the derivative is equal to 0. So we know anyway at minus 2 that we're going to be 0, and at 2 on 3 going to be 0. So it's just flat like that. Okay, if we put in minus 3 into our derivative, okay, we actually get that it's minus 11, so negative. Okay, for minus 1, we'll have to work that one out because I can't cheat from the textbook. Okay, and we say, well, f dash of minus 1 equals 2 take 3 times minus 1 times by minus 1 plus 2. So we get 2 plus 3, okay, and minus 1 plus 2 is 1. Okay, so we'll get 5, okay, which is positive. Okay, and then for for 0 we get 4. Okay, so we know that's positive as well. Okay, so we've got positive gradient, and then at 1 we get -3. So that was 5. So done that in the wrong spot. For 1 it was -1, it was 5. For 0 it was 4. Okay, and for -1 it's for 1 it's -3, so it's negative. Okay, you can see here we get overall shape there, so that one's going to be a minimum. Okay, and overall shape here is a positive, then 0, then negative. Okay, so we're going to have a maximum. So at x equals -2, we have a minimum. At x equals 2 on 3, we have a maximum. So a maximum. Okay, so we'll keep working. So the next work example is the curve y equals ax squared plus bx minus 24 has stationary points at -125. So calculate the values of a and b. Okay. So we know that the point 1 and 25 is on our curve. So what we're going to do is we're going to sub in those values directly into here. So we're going to say, well, we've got 25 equals a times -1 squared plus b times -1. Take 24. We've got 25 equals a, take b, take 24. Okay. That's supposed to be a -25. Okay, so that we get 1 equals a, take b. Okay. We also know though that at that point it's a stationary point, so what we need to do is we need to find dy dx. Okay, so we ignore our a and b for this, so we just we know x squared becomes 2x, so it'll become 2ax, okay, plus b, okay, for our derivative. Okay, so now we can sub that same point in here, okay, and say that we've got, oh no, sorry, not our same point. So we know our derivative is equal to 0 at that point. Okay, so we put in that our derivative is 0, okay, and when x is -1. So we say 2a times -1 plus b. So we get -2a plus b is equal to 0. Okay, so now we've got two equations here. We've got equation 1 and equation 2, and we can solve these equations simultaneously. Okay, so what we can do is we can bring our 2a across to say that b is equal to 2a. So now we can sub that into here and say, well, we've got 1 equals a, take 2a. So 1 equals minus a. So a equals -1. Sorry, I've mucked something up slightly there. -2a plus b equals 0. Sorry, this should be a -1, not a +1. Sorry, so that means that a equals +1. Sorry. Okay, so a equals +1, so b then equals 2 times 1, which is just equal to 2. Okay, so we know then that our value of a is 1 and b is 2. Okay, and if you like, you can say then that y equals x squared plus 2x, take 24. Okay, sorry about those couple of arithmetic errors. Okay, so we'll keep moving on. Okay, to curve sketching. So, if we're going to graph curves now, okay, or graph our functions, okay, we need to find the y-intercept by letting x equal 0. We need to find the x-intercept by letting y equal 0. We need to find the x-coordinates of the stationary point by letting our derivative equal to 0. Okay, we need to identify the stationary points by creating a gradient table. We need to calculate the coordinates of any endpoints for our domain. We need to identify if there's any asymptotes, and that's only if it's applicable. A lot of the time that won't be, and then we can actually draw our graph. Okay, so we're going to look at sketching this graph. Okay, so we're going to start off by saying our y-intercept. Okay, we've got to let x equal 0. So when we let x equal 0, well, this disappears, this disappears, this disappears, and we get that our y-intercept is when y equals -8. So that one's nice and easy. Okay, for our x-intercepts, okay, it's when y equals 0. Okay, so we're going to say 0 equals a half x cubed take 3x squared plus 6x minus 8. Okay, so then we can divide by half and say 0 equals x cubed minus 6x squared plus 12x take 16. Okay, so what we need to do is we need to find a factor. Because it's a cubic, we'll go do a bit of work here. Okay, but we find that 4 is a factor, so that means that x take 4 is a factor. Okay, when we do, what we would need to do from here is do the division of polynomials, okay, that we should be familiar with. Okay, just to save a bit of time and a bit of space. Okay, when we do our division of polynomials, we get 0 equals x take 4 times our x squared take 2x plus 4. Okay, so when we have a look at that, okay, then by null factor law, it means that x take 4 equals 0, or x squared take 2x plus 4 equals 0. Okay, when we actually have a look at this, our discriminant, okay, our b squared take 4ac, it's 4 take 4 times 1 times 4. We see that is going to be 4 take 16, which is minus 12. Okay, so therefore this part, okay, doesn't give us any solutions at all. Okay, so we're less than 0. Okay, so we don't get any. So the only one we're going to get is our x-intercept is going to be at x equals 4. Okay, so always be a bit careful, even though it's in this form. Okay, you could think that yes, we can factorise through, we're going to end up with 3 x-intercepts. Not always the case. So we know now that we've got an x-intercept at 4. Okay, to look at our stationary points, okay, what we need to do is find dy dx. Okay, so our dy dx gives us 3 on 2x squared take 6x plus 6. Okay, we've got to let that equal 0 now. So 0 equals 3 on 2x squared take 6x plus 6. Okay, easiest way here is we can take our 3 on 2 out as a common factor. So x squared minus 4 plus 4. Okay, which means we can say that we've got 0 equals 3 on 2 outside of x take 2 squared. Okay, so when we do that, well, we can divide by our 3 on 2. So 0 equals our x take 2 squared. Take the square root. Okay, 0 equals x take 2. So that's when x equals 2. Okay, so we know we're going to get a stationary point at x equals 2. Okay, so what we need to do as well is also find our y-coordinate of our stationary point. Okay, so we need to do f dash of 2. Okay, so we sub 2 into here and say, well, we've got 3 on 2 times 2 squared, take 6 times 2 plus 6. When we do that, we get minus 4. Okay, so far we've got our y-intercept, our x-intercept, and we're going to say our stationary point is now at 2 minus 4. Okay, we just don't know what sort of stationary point it is. Okay, now at this stage though, you should be able to go, well, hang on, I know what my stationary point is going to be, at least the nature of it, just don't, because we are a cubic. Okay, we're a cubic, okay, that has one stationary point. Okay, it's positive. Okay, so we need to do a gradient table, but we should know that it's going to be a stationary point that is shaped like this. Okay, because it's positive and we know we've only got one. But doing our gradient table, okay, well, we can go, we can pick, say, 0, 2, and 4. And what we get, well, we know at 2 it's 0, so it's flat. Okay, when we sub 6 into our gradient function, then we get 6. So when we put 0 in, we get 6, which is positive. When we put 4 into our gradient table, we also get 6 again, which is positive. And as we said, we know we're going to be that shape. Okay, so if you're cluey about your actual functions and the shape of them and what governs that shape, okay, then often you don't need to do the gradient table. Okay, so basically got everything we need now. So we know we come through at minus 8. We know we have an x-intercept at 4. Okay, and we know we've got a stationary point of inflection at 2 minus 4. Okay, so we know we're doing something like that. Okay. And remember, you should always be doing your graphs and things like that in pencil, in case you make a mistake. Okay, we've got a bit more to keep working with though, which is local and absolute maximum and minimums. Okay, so we can have a couple of different cases here. Okay, so we're talking about a restricted domain for these cases. Okay, so you can see here our endpoints. Okay, we've got an absolute minimum and an absolute maximum, which means our turning points is a local maximum and a local minimum. However, we can also have where our maximum minimums, our local maximum minimums, our turning points, are actually our absolute maximums and our absolute minimums as well. Okay, so there's a couple of different types. Or it could be 1 and 1. Okay, this could come down further, down here. Now this would be your local, your absolute minimum down here. This would just be a local minimum, but that would still be the absolute maximum. Okay, so you just need to be aware and check your endpoints of your function as well if you've got a restricted domain. So we've got one last worked example to have a look at. Okay, so we've got a function defined on a restricted domain by the rule y equals x on 2 plus 2 on x. Okay, where x is an element of 1/4 to 4. Okay, we need to specify the coordinates of the endpoints. Okay, well, all we need to do is sub these values into here. So we can say y equals 1 on 4 on 2 plus 2 on 1 on 4. Okay, which means we get 1/8 plus 8. So we get y equals 8 and 1/8. Okay, so one coordinate is going to be at, is going to be 1 on 4, 8 and 1/8. Okay, the other one, we go y equals 4 on 2 plus 2 on 4. It's going to give us 2 plus a half. It's going to give us 2 1/2. So our other coordinate is going to be at 4 and 2 and 1/2. Okay, so that's part A. Now attain the coordinates of any stationary points and determine their nature. Okay, so we want to have a look here and we want to find our derivative. So you say, well, first of all, I'm going to write this as a half times x plus 2 times x to the negative 1. Okay, and then we're going to find our derivative. dy dx equals a half take 2x to the negative 2. Okay, so then we've got to set that equal to 0. Okay, to find our stationary points. Okay, so we take our half away. Or actually it's better if I add this on and say that we've got 2x to the negative 2 equals a half. Okay, so think of that as 2 on x squared equals a half. Okay, so 2 equals a half x squared. Okay, and I'll just come up here. Okay, so that means that we'll have 4 equals x squared. Okay, which means we get x equals plus or minus 2. Okay, but remember what our domain is. Okay, only use x equals 2. Okay, and we need the coordinates, so we need to put this back into our original function. So we go y equals 2 on 2 plus 2 on 2. It's going to equal 2. So we have a stationary point, okay, at 2, 2. Okay, we haven't determined its nature yet. Okay, so we need to do that. Okay, so we need to set up a gradient table. So now we're at 2. We may as well choose 1 and 3. Okay, we know at 2 it's 0. Okay, and that we're just horizontal line for that bit. Now we need to sub 1 into our derivative function. When we do that, we get minus 3 on 2. Okay, so we know that is going to be negative. Okay, and when we sub 3 in, we get 5 on 18, okay, which we know is positive. Okay, and look, sometimes you don't really actually need to work out the values. Remember, you only actually need the sign of them. So sometimes your number might be a bit horrible, but you know it's going to be positive, so that's all you need. So I know now that our stationary point is a maximum. Okay, so we're getting there. Okay, sketch a graph of the function. Okay, well, we can't have a y-intercept because our domain doesn't allow it. Okay, and then if we have a look and see, and we don't actually have, we don't have it defined as a y-intercept, and there's no x-intercept since the endpoints and the minimum turning point all have positive y coordinates. Okay, so there's not going to be anything else. We know we don't have any other turning points, so what we can do is we can sketch it now. Okay, and our endpoint is 1/4 and 8.5. Okay, and then 4 and 2.5. Okay, and our turning point was at 2, 2. Okay, so it's just going to be something that goes like this. That's all we've got, so that's our 8 at 1/4. This is our 4 and 2.5, and this is our 2 and 2. Okay, so that's the end of this tutorial. So hopefully that gets you through sketching our graphs. We basically know how to sketch graphs. The only thing new here is that we need to actually find our turning points now. Okay, by setting our derivative to 0. Okay, solving for x, we're getting them, then we're finding what the nature of them are.